you. Thank you all for coming. I'd like to welcome you to the first lecture for the IGERT on Ocean Change seminar series, Topics in Ocean Change. For those of you who will be live tweeting during the seminar, the hashtag is UW-IPOC. Before we get started, we'd like to thank Jaseo for graciously providing travel support for our speaker.
And we're really excited to bring you our first speaker of the seminar series, Dr. Caldeira. Dr. Caldeira comes to us from the Carnegie Institution, Department of Global Ecology at Stanford University. He investigates issues related to climate, carbon, and energy systems, and is a widely published and acknowledged member of the science-climate community. Caldeira received his BA from Rutgers College, and then received his master's and PhD in atmospheric sciences from New York University. Following graduate school, he had a postdoc at the Department of Geosciences at Penn State University, and also had a postdoc in the Energy and Environment Directorate of Lawrence Livermore National Laboratory, where he also continued to be an environmental scientist through 2005 when he joined the Carnegie Institute. He's especially well known for his research on ocean acidification and more recent research on geoengineering and energy systems, and he's been recognized with many awards. One of the more interesting ones that we found was he was number 36 out of 100 agents of change in Rolling Stone magazine's April 2009 list of 100 artists, leaders, policymakers, writers, thinkers, scientists, and provocateurs who are fighting every day to show us what is possible. So today, Ken comes to us and he'll be talking to us about long-term perspectives and near-term actions relating to ocean acidification.
Thank you. It's actually amplified. I thought it was just going to be for the voice. So I'm going to, in this, is it possible to have the room volume down a little less? Because it seems too much for me. So, okay, so I'm going to be talking about ocean acidification in general, but the emphasis will be on coral systems, just because that's what I work on and we'll tell you a little bit more about. The volume control. Okay. Okay. So, the right computer. So we'll. And I'm gonna. You know, it was good, better before this time. This is softer. I'm just gonna put myself down a little. Okay. So.
Maybe put the microphone lower down. There might be a gain from the box itself.
Yeah. Okay. This is when you get a bunch of academics in a room. Here, we'll put this down. Okay. It's good? All right. Let's go with that. Okay. So I gave a special AGU talk this year, which they gave a whole hour segment to one talk. And so this is basically a retread of that talk. And so if any of you were in that room, forgive me. So let me just start off with an explanation of ocean carbonate chemistry, because even this is something that people get confused about all the time, because since they know carbonate minerals have carbon in them, then isn't the deposition of carbonate minerals a carbon sink, and shouldn't adding more CO2 help carbonate minerals precipitate and so on. And so just from a cartoon point of view, this is this over here is water, as you know. This is bicarbonate, and this is carbonate ions, and these two forms are the primary form in which dissolved inorganic carbon is found in the ocean. And so when we add CO2 to seawater, it first reacts with a water molecule to the carbonic acid, and this is unstable at the pH of seawater. And so when these protons tend to come off, tends to react with this carbon. So when people measure pH, and when they say that CO2 is causing the ocean to acidify, which is another way of saying it's causing the hydrogen ion activity to increase, or the apparent concentration to increase, then this is what they mean, that they're adding CO2 to, here, going back this way, adding CO2 to seawater and having this hydrogen ion come off. And one of the reasons why this is important for marine systems, this can be important on its own, But one reason it's important is because it tends to react with carbonate ions and thus decreases the carbonate ion concentration. And if you look at this representative of a calcium carbonate mineral, that you can see it's a calcium ion and basically a carbonate ion. And so when this carbonate ion is removed, this can become unstable and dissolve. And even if you don't get high enough CO2 concentrations and low enough carbonate ion concentrations to cause this calcium carbonate to dissolve, it can make it more difficult for an organism to produce a shell or skeleton. Okay, so then back in 2008, so let me just go back a little history here. That this had been obviously chemistry that was known since Roger Revelle and Keeling and all those guys figured everything out in the 1950s. And there was, people had thought a little bit about this ocean acidification problem, but people had done back-of-envelope calculations in the 1970s and said, okay, under sort of a business-as-usual scenario, the whole ocean will not become undersaturated with respect to aragonite or calcite. And I think just the fact that it wouldn't become undersaturated at that point was thought, well, then there's nothing to worry about. And then Joni Kleypas and a few others in the 90s had started publishing papers about the effects of declining aragonite saturation. And I think one of the reasons their work didn't catch on is just the language of calling it declining aragonite saturation levels just didn't catch people's attention. And then when people started thinking about it in terms of ocean acidification, it let people relate to it a little bit more. Yeah, let me just also say that at this point, the ocean is alkaline. It's pH more or less around 8, and it's going to stay with a higher pH than 7. And some people have questioned the use of the word acidification for an alkaline, basically an alkaline solution. And in the way I conceptualize it, acidification is like warming. It's showing a sign, and so the Arctic can be warming but still be cold. In the same way the ocean could be acidifying and still be basically alkaline. It's not going to be acid. Anyway, so we did this study in 2008 where we took the WOS, the WOS GLODAP gridded DIC and alkalinity fields, which represented a mid-1990s state, which I think Chris Sabine and others helped put together. And then we took out a reef base. We took each of these magenta dots represents a coral reef. And then we took our model result, which was a version of the GFDL MOM model, and backed out, did a pre-industrial to the future scenario, and then backed out of the sort of 1995 GLODAP numbers, the estimate of anthropogenic CO2, which for the surface is pretty easy, because for most of the surface ocean, the PCO2 of the surface ocean largely tracks the atmosphere. And so if you estimate what the aragonite, so calcium carbonate forms most commonly forms two forms of mineral in the ocean. One's aragonite and one's calcite. And these differ by their mineral structure, the crystalline structure, and aragonite is more soluble than calcite. And aragonite is also important because that's what coral reefs make their skeletons out of. So if we just take this plot, so this pre-industrial CO2 level map of surface aragonite saturation, and we plot on top of it the location of existing coral reefs, we see that something like 98% of coral reefs are located in places where the pre-industrial aragonite saturation was greater than 3.5, and something 99 point something percent were greater than 3.25 in this analysis. And so if we then march this, okay, so this is not to say that there's only one thing that governs the distribution of coral reefs, because there's other things that co-vary with aragonite saturation. For one thing, the amount of light is greater at the equator than at the poles, the temperature is greater at the equator than at the poles. And these things certainly have some role in determining the distribution of coral reefs. Nonetheless, if we march through this with time, so this is like a middle of the last decade, something like half the coral reefs are already less than 3.5 saturated. So this is open ocean waters. I should also stress that this is a coarse resolution ocean's general circulation model. So this is the chemistry predicted for open ocean waters surrounding coastal environments, but won't necessarily get the chemistry of the actual coastal environment right. Anyway, oops. So 380 by 450 ppm, so this will be in a few decades under a business as usual scenario. 550 under typical business as usual scenarios, a few, maybe a decade after mid-century, maybe a half century from now. And then, on these 650, 750 ppms are what you get with this by end of century with the business as usual scenario, where the colors down here, this pinkish color is representing undersaturated waters on the annual mean, so where things are actually dissolving. But the basic upshot is that under a business as usual scenario, there'll be no place left in the ocean with waters with the kind of carbonate chemistry that surrounded coral reefs through most of geologic time, and that even if you think that other factors such as temperature and light are important for determining the distribution of coral reefs, then you need to be quite an optimist to think that reefs will be flourishing under these conditions. So, so there's been observations of these things, obviously, since 1958, I think CO2 has been pretty well measured in the atmosphere. This is from Station Aloha, but now there's a few time series stations where you can see the PCO2 of the surface waters tracking the atmosphere and the pH going down. I always thought they should change a different pH scale. I think that looked a little more dramatic. But anyway, and now this has been seen in a few places. So the chemistry is pretty well understood, and really the question is really about biological responses. And this is just, just to point out, and I guess you here are well aware of this, that this is the western coast of the U.S., and this is Dick Feely's paper, that this has to do with the depth of undersaturated waters. Basically, the deep ocean is undersaturated with respect to most carbonate minerals, and the surface ocean is saturated. But in these coastal uplying zones, this undersaturated water can come up to the surface. And I guess there's a couple of things I wanted to say with this. One is, this is just to say that before, when I'm talking about open ocean waters, that the coastal environment can be very different. The other thing is how to look at the interplay of anthropogenic climate change, or anthropogenic change, I guess not climate change, anthropogenic chemical change, and natural variability. And I don't have this figure with me right now, but if if we think of the storm, so a lot of times, so let's say some undersaturated water shows up along the coast, and somebody asks, is that ocean acidification or is that natural variability? And there's more than one way to answer that question, and increasingly scientists are being asked to address this, climate change as a statistical phenomenon, but yet we're asked to comment on specific events. If we think of Hurricane Sandy, the waters off of, sorry, I know this in Fahrenheit, the water off of the coast of New York was 6 degrees warmer Fahrenheit than normal. And, but the global warming component of that was probably about 1 degree Fahrenheit, say 0.6 or something Celsius. And so, one way of looking at it is to say, well, the water was 6 degrees warmer than normal, and with climate change we'd expect 1 degree, so that it was probably 5/6 natural variability, 1/6 anthropogenic. But another way of looking at it is to say, okay, what's the return time? How frequently do we get water temperatures that are 6 degrees warmer? And that in a sort of natural condition, that 6 degree warmer waters might show up once a century, whereas 5-degree warm water might show up once every 25 years. And in that, so from that frequentist approach, you'd say, okay, that water this warm, that 3 out of 4 events of this magnitude we would expect. The probability of such an extreme event increased by a factor of 4 under global warming. So we'd say, well, that we can attribute 3/4 of this event to global warming, whereas from the sort of intensity approach, we say only 20% of it, or 17% is due to global warming. And so typically the studies that have looked at individual events that take an intensity approach have concluded that most of the event was due to natural variability, whereas the analyses that have taken a frequentist approach conclude that events of that, the main reason why events of that frequency are occurring is due to climate change. And so how you phrase the question, even given the same set of facts, can yield 2 different answers. And so, but I think this is the kind of thing that's going to happen, that, here it's showing 60 meters deep before you get under saturated waters. You're adding a little DIC to that. It's going to bring that up some meters and increase the frequency with which undersaturated waters are showing on the coasts. And the answer is going to be, well, it's some combination of anthropogenic CO2 penetrating the water and natural variability. And any particular event, trying to ascribe it to one cause or the other is going to depend on the details of how the question is framed and so on. And I guess there's another kind of question with these kind of systems, and that is, does this level of variability mean that you already have ecosystems that are adapted to high levels of variability, so they're already resilient? Or do you say, well, boy, these systems are already exposed to some pretty extreme events, and therefore they might not be that resilient towards events that are even more extreme. So this question of do these variable environments confer a higher degree of resilience or a lower degree of resilience, I think is not obvious. So, this is now a little old, but there's been a large number of experiments in the lab on looking at corals and how they grow as a function of aragonite saturation of the water that they're in. Some of this work was done in Biosphere 2. And basically, while there's some outlying experiments, more or less there's this fairly linear type relationship that seems to come out in a lot of experiments between the aragonite saturation state and the coral skeletal growth rate. And this, I know that Alex, I don't know how to say his last name, Gagnon, was just hired here, who's working on this stuff. One of the questions is that this looks very thermodynamic. If you just had a crystal in water and you were predicting how the precipitation rate of aragonite would vary with aragonite saturation, you would predict it to be linear. But if you look at the actual what's going on, all this calcification is going on behind membranes, in seawater, in altered seawater that's under biological control, and why. And then it's thought that the actual site where the precipitation is occurring, might be 20 times saturated, and that the organism is pumping ions. And if you start out from 4 times saturated versus 5 times saturated, and you need to bring it up to 20, the amount of additional work you need to do is a few percent more work to bring it up from 4 to 5, and you shouldn't expect sort of a 20% decline or a 25% decline in calcification rates if your mental model is that they're bringing the seawater up to 20 times saturated. So this question of why such a biologically controlled system looks so thermodynamic is unknown right now. And I know Alex, among others, is working on figuring that one out. And we've tried and been unsuccessful just through modeling. But anyway. So the other thing is that in a lab environment, you can actually dissolve the skeleton off of a coral and have a polyp without any skeleton, and it will live just fine. But the question is, can that organism survive ecologically when it's subject to predation, pressure, and so on? And so, this question of what, how relevant are the lab experiments to the field? In that, if we recall before, in the lab, people are growing corals at 1 time saturation, 2 times, 3 times saturation, but almost, very few corals are found in the field under those environments. And so one of the things that's happening in the field is that you're having all kinds of bio-eroders, that there's all kinds of organisms burrowing through coral skeletons, and there's fish chewing on the coral skeletons. And also there's just competition for space. And so if you have seagrasses and they're corals and they're trying to compete for the same space, that even if you put a fish tank with that chemistry there, the coral might be able to compete, but it might not be able to it might be able to survive, but it's not going to be able to outcompete, say, seagrasses to dominate that space. So anyway, just to say that people are going and now trying to do, this is not the corals, but they're trying to do field experiments where you alter the chemistry in the field or something closer to a field environment. And we're doing this, I'm not going to talk about it too much, but we're doing an alkalinity addition experiment next month on a coral reef in the Great Barrier Reef. So, not going through all this in detail, but this is a meta. There have been 4 recent review papers on ocean acidification, and this is a meta review paper where they review the 4 review papers, which is anyway. But yeah, the clearest case signal is with calcification, and in particular calcification in organisms that don't closely control their bodily fluids. So things like mollusks and corals and so on, where they're not tightly controlling their internal chemistry. There was something like a fish, where it's, a bone is not calcium carbonate, but it's producing, it's controlling its kind of internal chemical environment more. And so if we just zoom in onto the sort of survival and calcification, that it seems like in this set of organisms, the calcareous algae, corals especially, and I would say the corals is the clearest case. And I guess I'm not sure about every format these days. It's a funny thing in this business that in the beginning you can get somebody can get a paper in Nature by showing that it was negatively impacted by CO2, whereas now, if you find an organism that's not negatively impacted by CO2, then it seems to get more attention. So, so one of the things, so we did this set of, this maps using our GCMs and so on. There's only so much you can do with a coarse resolution ocean general circulation model. And so I had lunch with Jonathan Arias for dinner at some meeting, and he said, "Oh, you should hire my grad students, postdocs, and you should do field work." So, so Jonathan Arias said that there was a bunch of observations done by Donald Kinsey in the 60s and 70s, estimating the metabolic growth of coral reefs, and why don't we go back and try to redo some of his observations. And so I had some startup money on my job, which has since run out, and so I thought, okay, let's do that. And so one of the places that we did this work was this place called Lizard Island up here. Now, so the basic concept of this study, I can go through. The dominant water flow direction was this way. And so if you measure the chemistry here and you measure the chemistry there, and you know the flow rate, basically by the difference in the flow rate times the concentrations here minus the concentrations there is the net flux of material in or out of the reef or in or out of the gas exchange. And if it's alkalinity or calcium that you're worried about, there's none of the gas exchange flux. And so, basically the difference in these concentrations times the flow rate should give you the net calcification rate. There's a few other approaches, but that sort of black box, looking at this ecosystem as a black box, was the most straightforward one. And that's there's another approach also, but I won't go through it here. And so this is just a piece of what we did. It's taking some samples in a CTD currently here. So we did this twice, and basically, so this is sort of the numbers that Kinsey got in terms of calcification per square meter. We did it twice and 2 years in a row, and we got numbers that were around 40% less. This is the calcification. This black represents nighttime dissolution, which under the assumption that there was no calcification going on at the end of the night, so it could be a little bit more dissolution, a little bit more calcification. So, the reviewers and I, to the consternation of my co-authors, said, well, this is really anecdotal. And I think it's right that it is anecdotal, that we were probably not in the same exact spot that Kinsey was in, that the coral cover might have changed, that there's all these other kinds of things that can change. And so you can ascribe this necessarily to ocean acidification. And so I would call this sort of anecdotal evidence, but not that much stronger than anecdotal evidence. Now, if you went back to every place that Kinsey ever went to and you got the same kind of numbers, then it would be meaningful, but any one spot, if you don't know what the interannual variability is, maybe we just got 2 low years, or who knows what. Anyway, so we did another one, and this is where we're going back to. So this is sort of, the other one was closer to the northern end of the Great Barrier Reef. This is at the southern end. And this one is an interesting environment because this one forms this one tree island. It's kind of, the reef crest acts as a bath, it's kind of like a bathtub. So at low tide, water is coming out over this reef crest, and there's no water flowing into the lagoon. And so for a couple of hours at each low tide, this water is isolated. So that means that the change in the chemistry of this water is either due to interactions with the reef or air-sea gas exchange. And again, if it's calcium, it's not going to be air-sea gas exchange. Now, I'm waving my arms a little bit because there's also heterogeneity within this lagoon, so there could be circulation confusing things. But so basically what we did is at the beginning of each low tide, measured the chemistry somewhere, measured it again 2 hours later, and said, okay, what's the rate of change of the calcium? And from that we estimated a flux of calcium into the reef and get a calcification rate. And so this was published last year. Jack Silverman being my postdoc who led this. And so more or less, as you would guess, lots of calcification during the day, and that dissolution at night. Now, when Kinsey did this in the 1960s at the same location, he saw no nighttime dissolution, which dissolution is indicated by calcium or alkalinity concentrations going up in the middle of the night. And the confusing thing about this study was if we just stopped at the first one, life would be simple. But if we integrate over the daily cycle, we get around 40% or 44%, I forget what the number was, less calcification than Kinsey got in the 1970s. Except the thing is that we have a big increase in nighttime dissolution and a modest increase in daytime calcification. And so even though we're getting less calcification over the deal cycle, we're actually getting more daytime calcification than what Kinsey saw. And so, we just don't know what to make of it, is the basic story. So let me just say what we're doing next month. I won't go through the whole idea of it, but we're permitted to put a small amount of alkalinity into the seawater, and there's a big mess of how do you add alkalinity to the seawater without forming brucite. But anyway, we get to add some alkalinity to seawater as it flows over this reef crest. And we're going to take that same metabolic approach to see, as we add the alkalinity, can we detect an increased rate of coral calcification, which we think we will be able to. But unfortunately, with the permits, where everything's getting pretty close to detection limits, so we're not allowed to put in very much stuff. So this is just a picture of last time. This is the wrong number, should be 40%. Okay, so let me just go into a geologic context. So the way I actually got into all this stuff was my PhD dissertation was really on the chemistry of the end Cretaceous, of the ocean end Cretaceous extinction event. And at that time, nearly all calcareous plankton disappeared, as well as all coral reefs. And so the question was, if the marine carbonates are such a big part of the global carbon cycle, when you knock out marine carbonate secretors, how did the carbon cycle function? And that was more or less what my dissertation was about. But a lot of times people show a figure like this, and they say, well, gee whiz, CO2 was high in Earth's past, and there were plenty of reefs around Earth's geologic past, so what are you guys worrying about? And basically saying that isn't this an indication that these concerns about ocean acidification are overblown? And and I think it's really about rates of change. And so this is now getting a little old too, but this is the Vostok ice core record before it was brought back further, but it's the last 400,000 years of atmospheric CO2. And if you look at the rates of change, take each of these data points divided by the number of years, you see that most of this interglacial record is on the order of 0.1 ppm per year, 0.01 ppm per year, but it's sort of measured in the hundredths of ppm per year. If you look at, for the last few decades, it's trending up. I should update this one, but it's, getting close, say 2.5 ppm per year. So it's sort of 2 orders of magnitude faster than most glacial, interglacial CO2 changes. And if we put these two things on the same figure, there's a few points that jump out. But basically now the kinds of atmospheric CO2 changes today are roughly 2 orders of magnitude higher than the changes glacial, interglacially. And so we did this. This is a set of simulations of where we burn. I think in the first IPCC report, they said there were 3,400 petagrams of fossil fuel resources. And then I think the next IPCC report said 55,000 or something like this. My understanding is the next one's going to say 12,000 petagrams of carbon. But this one, we took the sort of the one IPCC number and divided it by 2,500, 1,250, and then doubled and quadrupled. This question of fossil fuel resources, by the way resources are defined, reserves are actually identified commercial deposits, but resources are fossil fuel resources are fossil fuels for which a conceivable future technology could economically extract them, reduce carbon, and so a lot of what you count as fossil fuel depends on your conception of future economic conditions and future technology and so on. And so, for example, whether you thought fracking would come along or not, you might have 2 different estimates of natural gas resource sizes. But basically the next generation of IPCC would put a burn it all scenario somewhere above this blue line. If we take that this glacial interglacial curve and we try to squash it down onto this same scale, is that sort of glacial interglacial, and this is kind of the magnitudes that we're facing for the next decades under a business as usual scenario. So I mean, even this anyway. Just to say that what we're doing, just in terms of magnitudes, is large compared to this is not large compared to the Cretaceous to the present, but certainly large compared to glacial, interglacial. Oh yeah, and if we go back, this is from Mark Pagani's, and Jim Zakos's, most of Mark Pagani's work. I'm forgetting to give it one. Sorry. So, but anyway, this is the numbers of PCO2 that you go get to burn different amounts, and this is the log scale. And this is for two different independent attempts to reconstruct atmospheric CO2 over the last 20 million years. And more or less they get that for the last 20 plus million years, atmospheric CO2 has never been greater than today. Here's 100, 200, 300, 400 ppm. That, and so both in terms of magnitude and rates, that we've pretty much exceeded what's gone for the last few tens of millions of years. Let me just, I don't have slides about this, but, obviously some of the, Dave Archer, who's an alumni of Emerson and so on, that the key work on timescales for neutralization of CO2 that we add to the system is really, I think, largely came out of this MUDS model that Dave Archer did. And I mean, other people have done this work before him, but I think Dave has really focused on it. And then that if you add CO2 to seawater, what did I say the surface ocean in the tropics is easy to predict the future chemistry of? Because if it's not that different than if you took a bucket of seawater and put it under a bell jar and just change the CO2 level and let it equilibrate. Because that water is isolated from the sediments, and I should make a different cartoon, but if instead of just, once we've dissolved, in that first cartoon, once we've dissolved that calcium carbonate, now the negative charge on the dissolved inorganic carbon is balanced by the calcium ion and not by the hydrogen ion. And so if you allow the carbonate minerals to dissolve, then the amount of chemical change caused by an addition of CO2 is much less. And so then the question is, well, how fast does that process happen? And if you think just in rough terms that it takes on the order of, say, 1,000 years for the ocean to fully turn over, and then something might have to take several transits. Most of the ocean's not touching sediments; it's in the middle of the ocean, and so it'll take several transits for it to contact and equilibrate with the sediments. And so we're talking about several ocean overturning times. And Dave